Welcome back. Today we are going to use the rhoCentralFoam solver that is present in OpenFOAM. It's an open source software. This particular solver, as you may have seen the introductory lecture, where I explained that rhoCentralFoam is a density based solver and it solves the variables, the pressure, velocity, and energy in their conservative forms. The conservative forms are density, momentum, and energy. Using that, we are going to simulate the shock tube problem, rhoCentralFoam. As I said in the introduction as well, that it can only handle meshes which have a mesh resolution which is changing gradually, or it has a constant mesh resolution, and it can capture the shock very well. In order to simulate a shock tube problem, I'll also explain what is a shock tube problem. I'm going to copy the cavity problem, or we can directly copy the shock tube problem that is already there in OpenFOAM, and I'll just go through the solvers, the source code of the solver, as well as the entire setup, and I'll explain the problem and how it is set up. So let me also open this. So the folder is already open in the VS Code. Here we have the various directories that are required to run any simulation in OpenFOAM. I'll first copy this o.org. Actually, I can use this all run file to run this particular simulation, but since we are going to go through this particular setup in a step-by-step manner, so therefore I'm not going to use this. Let me first copy 0.org to 0. So you can see now we have two folders. These are the three folders that are essential. Now, first let me talk about the mesh. Here, if I run blockMesh, I can see the mesh. So I am creating this mesh because I first want to talk about the problem. Here we have this particular block which represents a 1D domain. Even though this looks 3D, but if you look at the mesh elements, you can see that there are only one mesh element along the y and z axis, and there are multiple mesh elements along the x axis. Along this axis, you have some n number of elements. Here in the shock tube problem, you have a uniform velocity in the entire domain, but at the middle, before this, you have some different pressure and temperature, and after this, you have something else. That creates a step change in pressure as well as in temperature. Here you can see how you can create a block mesh using a blockMesh dict file. If you don't know how to create a block mesh using blockMesh dict, there is a tutorial that is present in our YouTube channel. You can go there and watch that particular video. Here how you create a hex block out of these points, and then these are the boundaries. These boundaries are sides along the x-axis, which has normal along the x-axis, and then all other sides which are along y and z are labeled as empty, because along that direction we do not want that direction to affect the simulation. In this way you can set up a 1D simulation. Now the second step is, after you set up all these things, you want to set up that what is the pressure till half of the domain and what is the pressure after that. For that you should use this setField dict. In the setField dict you can set the values for velocity, temperature, and pressure, and these are the values. And similarly for regions, then these are default values, and for some particular region you want to change these values, you can do that by setting up like this. Here the method is used is box to cell, where you have to define the box, the initial point of the box, and the point which is diagonally opposite to this point. This will define a box. This covers the entire domain in the y and z direction, but in the x direction it is starting from 0 to 5, but our domain along the x direction is from -5 to 5. Therefore this is half of the domain. The domain from 0 to 5 has the temperature value 278.746 and the pressure value like this. Now we'll look at how we set up the solver. In order to set up the solver, you have to first define the solver name here, and these all other parameters remain same for all kinds of solvers. You can change this depending upon how long is your simulation, how stiff is your simulation, which defines the delta t for that particular simulation, and then how you want to write the results and the right format and various other things. Then these two files are very important, fvScheme and fvSolution. In the fvScheme, these all you will find in almost all the solvers, but this is something which is specific to this rhoCentralFoam solver, which is the flux scheme Kurganov. This is the flux scheme that governs all the dive schemes. So you can see the dive schemes is empty, even though you have pressure, velocity, energy, and you may have other turbulent properties as well, but these are not defined here because for all the flux calculation, which are essentially the dive scheme, a flux scheme is used, which is Kurganov. And for interpolation, unlike linear interpolation, which is used in most of the incommensurable solvers, there is a different kind of reconstruction is used, which is von Leer, and for vector it's von Leer v. For scalars again von Leer. These reconstruction make sure that your reconstruction is slope limited, and also the entire scheme is total variation diminishing. You have to make sure that you use this kind of setup only. Everything else you can see is as usual, Gauss linear for grad scheme. The DDT scheme is Euler. Then in the fvSolution, these are also very straightforward. This is a diagonal solver. That means it just takes the diagonal values and try to approximate the values by taking the diagonal values as a dominant term. And then for velocity, it uses a smooth solver. That means it also takes the values which are off diagonal and use Gauss-Seidel kind of solver. And for h, it uses the same solver as used for velocity. So this is the entire setup. Let's see how you can set up the constants that are required for the simulation. If you remember from the introduction that there are various closures that are required. For example, the relation between pressure and energy, the relation between energy and temperature. These are all defined here. If you are not sure that what these mean, you can look at the introduction video, which was posted last week. And then you can also set up these, which are the definition of various parameters. For example, the mole weight, which is required to evaluate the equation state, and the R value, the gas constant, and then the thermodynamic parameters. Since this is constant, then what is the value of Cp? If it is not constant, then the initial value is required, and then it changes according to temperature. And then there is this HF value. Similarly, for transport, there is mu and the Prandtl number. So these are all required. This one you can skip because this is the energy of formation. This is not required for shock tube problem, but again, if this is required in any of the simulation, then it will be taken as a constant from here. Then for turbulence, we are considering a laminar simulation for shock tube. And for shock tube, it's a very simple flow and it's density based and everything is solved explicitly. There is no need to introduce turbulence, but the rhoCentralFoam solver can handle turbulence on k omega SST models. You can pass those models. They are not very robust with rhoCentralFoam solver. If you really want to solve some turbulent flows, then you have to switch to rhoSimpleFoam or SonicFoam. Now let's talk about the boundary condition. The boundary condition for pressure is that for the sides, for you can say the left and right side where the shock is going to meet the walls, we consider this zero gradient and empty are empty. Similarly for temperature and velocity, there is no difference. And here you can see that the temperature is set as 1 for the entire field and this is set as 0, but this will get overwritten by this dictionary. We'll see that how we can run this. We can run setFields, and now if you look at these, so you can see all these values are populated. Similarly for temperature and velocity. Now let me run this. So we can run this by typing rhoCentralFoam, and let's look at these results. You can see at 0.001 This is the pressure, and if we just play it, you can see that the shock was going in this direction, and on the left side we have expansion wave. You can also look at the plot of this by going to filters, then plot over line, and you can set up this as 0, 0, 0, 0. This is for pressure, and here you can set up that what lines you want to be plotted. I want temperature, velocity. No, let's look at just velocity magnitude. You can see that this is the shock wave, very steep gradient on the left side, which is here, and this is the expansion wave. Similarly, let's look at temperature. For temperature, you can see again for the shock, and this is the contact, and this is the expansion wave. Similarly, for rho, you will see that there is a contact. Expand this. Here also you will see that this is the contact, this is the expansion wave, and this is the shock wave. Let me run this from start. This is the initial condition almost. Then you can see this is the shock wave, this is the contact, and this is the expansion wave. And as the time progresses, you can see all these. You can also plot these against a known solution. For that, you have to write a Python code, and if you want a solver for this, you can go to any of the textbooks, or you can search online. You can find the exact solution of this Riemann problem, and then plot that solution against this and compare that how accurate is this. One thing to note here is that you see these oscillations near the shock wave. These oscillations, these are the results of the presence of this shock and the inability of the scheme to capture the shock properly. For this, there are various methods. For example, one of them is you can introduce artificial viscosity, which will reduce these kind of oscillations near the shock wave. And there are other schemes as well that you can find in the original version of the OpenFOAM. The original version as in the OpenFOAM, which is handled by the OpenFOAM Foundation. The version which I am using here is the one which is handled by OpenCFD, which has different schemes and they are more industry oriented. And the other one, OpenFOAM Foundation, you can also use it for your consultancy projects as well, but it is more research oriented and it has continuous development version. Now let's look at the source code of rhoCentralFoam solver, and let's see how it is different compared to rhoPimpleFoam, for example. Let me open that. This is the source code for OpenFOAM. If you want to just verify that which version are you using, you can go to etc and then bash rc. Here you will see that this is the version from OpenCFD Limited. Then to look at the source code of the solver, you have to go to application, then solvers, and then compressible. And here are the solvers: rhoCentralFoam, rhoPimpleFoam, rhoSimpleFoam, and SonicFoam. Let's look at rhoCentralFoam first. And this is the rhoCentralFoam. It starts with this, the main. It is including all the checks here, right? All the headers which are required for this particular simulation. Then it validates the turbulence model or the coefficients, and then it starts running. Here you can see the runtime.run. It checks whether the final time has reached or not. If it has not reached, it is increasing the time and doing any kind of mesh update. For example, if the mesh is moving, then it will update. Then you can see here that these are the variables on the positive and negative sides: psi value, energy, velocity, and then pressure. And then after making these variables, it is solving them. Here it is calculating the square root of this, which is gamma. That means this is the speed of sound, c. And then it is checking if the scheme is this one, then it will calculate like this and then solve for density. You can see that it is taking this particular solver, which is the ddt of rho plus the divergence of phi. So that means this is an explicit equation, and then eventually it will then do all other stuff which is if it is not inviscid, then it do these steps. You can check the equations. If it is not inviscid, then it runs all these as well, then some boundary correction, and then end loop, and it goes back and do these steps again. The details you can go through them one by one, but the main thing to note that here is that these are the conservative variables, rho u, e, and these three only. So it is using these values to evolve the conservative variables and to evolve the system. But in case of rhoPimpleFoam, you can check here and go to rhoPimpleFoam. The process is different. It starts with this initial pimple loop. Here the velocities are predicted and depend upon the updated pressure, and then using this it satisfies the continuity equation. You can go here, the rho equation is this, which is the continuity equation, and then once it satisfies the continuity equation, then it corrects for pressure. You can see clearly that the rhoPimpleFoam is basically using the pimple method to solve for compressible flows. However, the rhoCentralFoam, it uses the explicit time integrator and evolves the conservative variables, which are the rho, the momentum, and energy. I hope this is clear, and let me end this lecture here. And if you like the content of our channel, then you can like, share, and subscribe. Thank you.